Hello, good afternoon. Yes, here is old man of the clan. Hope Sunday is okay. I hope all of you went to church and got some lessons for the week. I think 2 days ago, I think I promised, because I explained something briefly on Skew deck slab, and I said I would add some more explanation. So what I did here, I tried to look at three different types. I have normal. This is 6 meters by 10 meters. This is skew. The second one here is skew, 10 degree skew. No, 15 degree skew angle. This is 20 degree skew angle, and I jumped to 30. So I wanted to look at how change of skew angle affect the response of deck slab. So here is exactly what I did. I did a model, gave all these nodes support system just for understanding the behavior, just for a typical slab. And then I considered self weight, and then also the traffic load. The traffic load I adopted is HB 25 and normal HA. Of course, the software put in that. And I used a single lane. I wish I could see display. So the good thing with MIDAS is it allows you. Now I have 4 different deck slab on the same screen, and I applied all you see all this lane are given, and then you put in the vehicle, all these vehicle types, and the rest of it you apply, and then afterward you do what you run and give you the output. So from the analysis you realize that when you run the design, you look at the deformation due to self weight, and now definitely you'll find that but before that, let me remove the lane. I think good. So this is deformation due to self weight of the different self weight, but of different angle. This is for 15, this is for 20, and this is for 30. So when you look at the deformation effect, you can actually see how the whole thing changed. Now, if I apply or allow the traffic to go through, and then you look at what the traffic does. So this is the implication when the traffic is moving. So I think I could actually look at minimum deformation and maximum. I think they are not all that different. They give you more or less similar contours. Yeah, so I think the deformation, this is basically downwards. Yeah, so basically that is what you could actually see. In terms of reactions, I also realized that the reaction do vary. Even due to self weight, the reactions are not the same, but they're the same for the normal deck, which is this one here, the first one, and they vary. You can see here, this is uniform, the same values, and as soon as you move to 15 degrees, the obtuse angle I told you yesterday tend to give higher value than the acute angle, and the value also tend to vary. As you increase the angle to 20, you can actually see the value also increases. So it seems the reaction value at obtuse angle for skewed deck increases with increase in the skew angle, and with a lot of twisting and shear forces, you're going to see the output the other side. So then this is now for 30. For 30 now it is in 200. So you can see it has gone up by almost 46 from 62. It doubles. As soon as you move the 10 and 15 degrees, it doubles. And then as soon as you increase further, it goes higher. While the acute tend to reduce, you see, tend to reduce to 17, and then here to 10. So obtuse angle increases while obtuse angle reaction increases, while the acute angle reduces as you increase the. So that is due to self weight. What about when now you apply the traffic load? Would it also do the same? Okay, so angle is the same actually, but the increase is not as much as the self weight. The increase is from 40 to 50, I think in the magnitude of 10, but it jumps 50, it goes to 20 something, 30, actually 36. So in a way, also there is also observation of increase while reduction in acute angle. And also those are, if you look at this, you can see that all these are varying. This one is due to, but when you go back to self weight, this one look uniform. This one tend to go slight, obtuse angle tend to go higher, and then reduces in a way, and normalize, all that tend to reduce. But as soon as you put because of the traffic and different because of KL and HB, it's not like all uniform like the self weight, the weight is linear, no. And you can actually see that one of this is lifting. So this angle is already being lifted. This is negative value. So you have to be careful that to some extent there is also lift in the reaction value in certain instances for when you're increasing the skew. But at least it is certain that they are not uniform, and therefore when you're designing and you're reviewing, take note that the things are not uniform in a way. So this is for the reaction. What about now when I look at moment? When I look at moment forces due to self weight, maximum moment. This is how the maximum moment would look like. So for a normal, you can see the normal distribution, you are linear in a better way. And also I realized that within 15 degrees of the skewness, most of these patterns tend to be similar. I also hinted on that yesterday. But when the angle increases from 20 and above, from 15 and above, there is a tendency you are going to see that even the shear force and moment tend to start hogging moment or edge. The hogging moments at the end here tend to increase. So that is what we need to be aware of. So when I look at the traffic, how does it behave? This is how the traffic load will behave on the skew deck. So you can see that this is more or less similar, though there's a shift. This is uniform, but there's a shift. So when the angle goes to 20, also it is shift further, and then also the acute angles tend to be mild, and then these forces will tend to move there while there's a shift. Of course, because of the axial loads and the UDL, we don't we need to expect some of the things. Then we have definitely now this is the 30 degrees. So if I have the angle, if I look at cut sections, you realize that the normal deck slab has a 170 bending moment with a slight edge moment or hogging, and then the diagonal moved to 175 with a slight you can actually see here that we have moments here. So this is diagonal, and there is also some moment here. So we have to be a bit careful, especially for this is for the normal. So more so it is actually bending of which happen. But when you change and move to 15 degrees, you definitely find that actually there's from 4 to 14, the edge moment or end of the beam, or what we call hogging, there is also moment there. That means your reinforcement need to be bent in a way to take care of the stresses at the end of the deck slab. So it is very important, and that's why we were saying the use of U bars is very important to take care of that. So it is 14, while at the obtuse angle it moves up to 42, from 10 to 42 4 times. Then when you move to the 20 degrees, it is now 15 for the normal straight, and then at the obtuse angle it has gone up to 54, while the moment there is this moment redistribution. The bending moment of 175 start reducing to 160, and then you get a 42 kilonewton meters at the ends or at the edges and corners and obtuse angle. Then as you move your angle to 20, definitely also it has moved from 42 to 54 by also about 10, and then the bending moment tend to reduce to about 150. So, and now when the angle continue, and you find that actually the load tend to narrow or reduce to 2 kilonewton meters, but at the obtuse angle, the moment tend to be higher than the rest, and there is a redistribution here from 170 by that almost by 30 kilonewton meters. So this is very important to always take note of, as especially when you are doing quality assurance and you are the main guy reviewing a design. A designer can do his thing, but you need to take note areas that needs a bit of special attention. What about the shear force behavior? So this is how the shear force pattern, you can see the pattern changes. You have 75 at the normal deck diagonal, so it's basically 75 all around in a way. Then you have 222 and then 157. So we have 82. This is for a 15 degrees skew angle. You can see there's a jumped almost by 3 times, from 75 to 225 or 223 there. And then when you increase the skew angle to 20, definitely you can see that there is a redistribution of this, but the shear value tend to start reducing, but no, tend to redistribute, but higher on both. Here one side was lower by almost close to 50, but here it is 216 and 201, and therefore you can see now as you now move beyond 25, you can see that basically the skew and obtuse angle tend to have similar values. So there's and even towards the midpoint. So in a way, this also is important to understand. So it is very, very interesting event. In terms of stresses, if I look at the plate and due to, okay, let me remove that due to that. So these are stress values, though I would actually put and then maybe try and see if I can get and then I put the values and see if it is not over congested, so no need for that, but you can look over from here. So you can see 0.9 for the traffic, and then so these are stress distribution at different angle. This is 15 degrees, this is 20 degrees, and this is 30, and this is due to the live load. So if I do dead weight, what happens? What I didn't tell you is the dead weight is I've used a thickness of 1 meter. Of course, you can still vary. So this is the stress distribution you have when you have self weight, and you can see the pattern are not the same, and yet the length, this horizontal length here, is actually about 10 and 6. Of course, the skew angle will be different. This skew distance will be different, will be longer than this one, but the vertical one would still remain there. So these are some of the observations that I thought I would actually add on to what I explained earlier, so that you pay more attention when you're dealing, even when you're dealing with box culverts. You have skew box culvert, you need to be a bit careful, especially dealing with obtuse angles. What we have to cross-check, which I've not done, is if I have T-girders, shall we have the same stress distribution, or there will be a difference? Because now you have a beam which tend to concentrate loads on the bearings. So that is something that we need to pay attention. Otherwise, I think this is basically what I thought I should add, so that you are able to do what? You are able to see and then look at. So this is just animation, just to show what happened, how the stresses get distributed on the normal deck slab, the 90 degree, to a 15 degrees skew angle, to further degrees of 20, and then on this one. That also helps because I told you there is twisting, there is moment, there is shear, axial load. So this is due to self weight. What about if it is due to live load? Due to live load, sorry, if it is due to live load, I will quickly look at that and then put animate. Okay, so this is how our live load stress distribution would be, and as the vehicles are moving across, this is what happened. And so we need to be mindful of that and pay attention, especially most these young engineers who are coming on board, that there are many things that we need to, even I think maximum forces here, I think, let me see, okay, I think force fx is not there, myy, this is myy, similar mxy, okay, then so the m maximum is similar to this, and so it does not match. Yeah, okay, basically I think that is what I thought I should be able to explain that. So I think I'd actually summarize something and I put it here, which I think is similar. I don't need to waste much of your time. I had actually put in the 3D model for the normal and skew deck slab bridges, and then I also indicated here you have the skew deck, or the skew angle of 15 degrees. You have seen how the load varies, skew angle of 20, 30, and then the normal. Assessment of deck response was done, and then this is the output that I had given, which is similar to what I've demonstrated direct from the software. You can look at it. So the patterns are not the same. That is the most important thing. The patterns are not the same. Please let us pay attention and then try to look at all that. So these were the reactions that I did. So basically I think that is that. So skew deck, and there is something I need you to read. It's about aspect ratio. The aspect ratio, because I think it is to do with the length and the length and then the width. I will check which length is considered and which width is considered, so that you get, because most of this aspect ratio guide the engineer to determine the width and the depth of if it is a slab, to ensure that it is done correctly. But otherwise, this is very important. Pay attention in detailing, Be aware of your obtuse angle. They tend to be overstressed when you are loading and when the angle is being hot, the angle is being increased. Please enjoy your weekend and enjoy the start of the new week. Look at it. Any more information we shall share as we share our experience and exposure. Thank you so much and have a good weekend.